Okay, today we are going to learn an important derivation for the board exam. So here is the derivation. We are going to learn about how to derive an expression for electric field due to straight infinite long charged wire using a Gauss law. Here there are three important terms, that is electric field. We are going to find expression for electric field and for a infinite long charged wire, and we are going to use a Gauss law for this. And we can find here there is a wire, and it is of infinite distance or infinite in length. On this wire we have a positive charge which is uniformly distributed. You can see here all the positive charges are uniformly distributed. So when the positive charges are there, it there creates an electric field around a wire. Okay, so we need to find a given point, or we are going to take a point P somewhere here around the wire. So there we need to find the electric field intensity. So by since we are using a Gauss law for this, so what we do, let us take a point P here, where we need to find electric field intensity at this point. So for that we need to consider, when we consider point P, there we need to consider Gaussian surface. The Gaussian surface will be in the form of cylinder. Okay, because we are going to take a part of the length here. We're not going to take infinite length, so we're going to take a part of the wire that is of length L. So we are consider the length L. Okay, only L we are going to consider. So now the Gaussian surface is what? We have a cylindrical surface as a Gaussian surface, like around the any wire. Okay, so now our aim is to find the electric field intensity at a given point. The point P is here. So what is the distance we have? A small r, okay, from the wire to a point P. And the Gaussian surface is cylindrical surface, and the length for this the length of the wire is L we have here. So let us see what all things that we have learned now. Okay, by seeing the diagram, so what we have understood, that we are going to write as an description of the diagram. So let us see in a short form how we can write the description of the diagram. So now we have considered here an infinite long thin wire with a uniform linear charge distribution, and we have one formula, linear charge density. Okay, that means that is nothing but for a this is the length of the wire, and per unit length, suppose if I have a small as a unit length, for that how many charges are present. Okay, from here to here it is a complete length that we have taken, and example like 10 centimeter we have taken as a length, and we need to know what is the charge present for 1 centimeter, that is a unit length. So that we call it as a linear charge density. Okay, so now that we are going to represented by, that is going to represent by that is represented by lambda, that is a linear charge density, and we can simply write as delta Q by delta L, or we can simply write as Q by L. So this describes how many number of charges present per unit length of the wire. Okay, I hope you understood. Like 10 centimeter in length, we need to find how many charges are present in 1 centimeter in length, like small part here. Okay, how many charges are present, so that described by linear charge density. So now I hope you have understood this line. Then what else we have? We have considered a point P where it is present at a distance r from a wire, so that you can include here. So at point P, what is our aim to find? Our aim is to find electric field at this point. Now let P be the point at which electric field is calculated. So it is simple as that. So we need to find electric field at this point, or electric field intensity at this point. Okay, so now construct a imaginary cylinder or Gaussian surface around the wire such that P lies on its surface. That is what we have done here. So first we have taken a point P. From there we have taken a Gaussian surface which is in the form of cylinder. Okay, so like you can consider for an example, like comparison to understand more clearly. So we'll take a tube light as an example, like to make ourselves understandable. We have taken a tube light. So there what we are going to do, we need to find a tube light. From the tube light there is a point P. We need to find out what is the intensity at that point. near to the tube light, like that. So for just for a comparison, okay, so this is the same thing that we are going to do. We need to find electric field intensity at the point P. Now we need to know some formula here, that means electric flux. Okay, by the definition we have electric flux formula, that is electric flux is nothing but for a given surface. Like suppose we have a point P here, we have a small surface, okay, which is like this, and at this point or at this surface, how many field lines are moving. Okay, usually why we are taking this, all the electric field that is represented by electric field lines. Okay, so always from the positive charge it emerges out, the electric field line will emerges out. So that means all the electric field line passing through this surface, this is the surface and it is passing like this, right? So now how many field lines are passing through the given surface, that is known as electric flux, right? So let us see how we can put this into a mathematical expression. So this delta flux or delta phi, what we can say, what it describes as how many electric field line which is coming out from the surface. It delta means delta or d psi, it's a small unit or a small number of electric field lines which is coming out from out of the surface. Okay, it's a small surface and small number of electric field lines are moving away, moving through the surface. So we have E into delta S cos theta. Okay, delta S is nothing but the small surface present here, that is a delta S, and E is the electric field intensity at this point, and delta flux is a number of electric field lines passing through the small surface. This is a small surface we can say. Okay, the delta that is represented by delta S, or also we can represent as a d flux or d phi is equals to E ds cos theta. The ds is nothing but the small surface here. Okay, d flux is nothing but the small number of electric field lines passing through this small surface. Okay, so what is this cos theta? Theta is the angle between the area vector and electric field line. Okay, so the area is here in this, it is the surface. Okay, so always the area vector is perpendicular to the surface. This is the area vector along with the in the direction of electric field lines. Okay, so what is the angle between area vector and electric field lines? Okay, so think about that. So this is the surface and area vector is in this direction. Also there is electric field line in this direction. So the angle between area vector and electric field direction is 0. Okay, there are two vectors here. Okay, so what you can expect as theta is 0. Okay, so you know that is, I'll just repeat this, okay, because it is very important. The area vector for this surface is in this direction, and also there is an electric field line which is directing in this direction. Okay, there are two vectors here. The angle between electric field direction and area vector is, that is called theta, and that is 0. Okay, that is 0. So that is what we have taken, theta is equals to 0. Then what happens to cos theta? Cos 0 degree is equals to 1. Okay, that means there is a maximum number of field lines which is passing through this small area. That is what it signifies. Okay, so our expression becomes d flux is equals to E ds into 1. Moving to the next thing, that means we don't need small electric flux. Okay, that means small number of electric field lines are passing through this surface. Okay, but we need a total electric flux. That means the total number of field line which is passing through the entire cylindrical surface. Okay, so for that what we do, we will integrate it. Okay, if we integrate d psi, so what we get a psi. Okay, if we integrate a small flux, we get a total flux. And if we integrate here in this at the right hand side of the equation, so we'll keep it as it is. So integration of E ds, that we have kept as it is. Okay, so this equation we get as flux is equals to integral of E ds. Next, now So we have just marked integral of ds. Okay, that means if we add all the small part of the surface, like if we add all the smart of the part of the surface, what we are going to get. So if we integrate ds, so we can consider the surface area of the cylinder, right? So if you that means if you take summation of all the surface, we'll get a surface of the cylinder. So that is what it means here. So now what is the total surface of the cylinder? We have integral of ds is nothing but 2 pi rl, that we have learned in our the previous, like in a basic classes, right? Integral of, or the total surface of the cylinder is 2 pi rl. Now we're going to substitute this thing, that's it. Okay, so see here, flux is equals to E into 2 pi rl, that forms the equation 1. Okay, and so this is the formula for a flux that we obtained from a definition, and we have another formula for flux, that is from a Gauss law. So let us see what is the another flux formula by using a Gauss law that we have got. So flux is equals to 1 by epsilon naught times q, that we have as a flux definition according to Gauss law. Okay, so these two formula we have. Okay, flux is equals to E into 2 pi rl, and flux is equals to 1 by epsilon naught into q. So now what we are going to do, equation 1 and 2, we are going to combine this. Okay, so now from the equation 1 and 2, what we get, so we just substitute, instead of flux here, we're going to substitute this part. Okay, so flux we have substituted 1 by epsilon naught into q. So that is what we have done. 1 by epsilon naught into q is equals to E 2 pi rl. Next is, we want to know what is the electric field at this point, right? So from the given from the equation, we have E here. We are going to find what is E. So simply you just take this 2 pi rl to the denominator of the other side of the equation. So now what we get, 1 by epsilon naught into 2 pi rl into q is equals to E that we get. Have you remember, we have learned one small derivation in the beginning. Here you can see here lambda is equals to q by L, that we are going to substitute here. So what happens to q now? I want to know, I have lambda is equals to q by L. I want to know what is the q value. So what I do, q is equals to, we'll take L to the numerator, that is lambda L it becomes, right? So that is what we are going to do here. See, according to linear charge density, we have lambda is equals to q by L, or simply we can say q by L. And we know that q is equals to lambda L. That is what we have done. So we have taken L to the numerator. Next, we are going to substitute that in place of q. So what we can substitute in place of q? That is lambda L. So that is what we are going to do. So in place of q, we are going to substitute lambda L. Then we get L and L will get cancelled. From L from the numerator, L from the denominator will get cancelled. So we get lambda divided by 2 pi epsilon naught into r. So this is the final equation that we can get, and we can write that in vector form, that is E vector is equals to lambda divided by 2 pi epsilon naught into r into n cap. This is the direction of an electric field. Thank you.